So, dear students, today we will learn the Raman spectroscopy. When a beam of light, okay, suppose we consider the monochromatic beam of light. Monochromatic means which is having only one wavelength is there. When monochromatic beam of light incident on sample, there is a scattering of light takes place, and some light is transmitted. Okay, scattering means when light that if suppose that is a molecule is there or a substance matter is there, it will strike on this and at some angles it will scatter. Okay, number of there is scattering is observed. Okay, and these scattering lights may have, if suppose that light has the energy is equal to h mu, in this mu is frequency. Okay, therefore we have written mu as mu I, means I stand for the incidence frequency. When light falls the samples, the light is scattered, and that scattered light may have the energy h mu frequency. Okay, the same frequency, a light strike on this molecule, the scattering takes place, and that scattering light can have the same frequency of incidence light, and we have given, okay, that is h mu I, that is same frequency which is having for this scattering light. If such scattering is there, that scattering is Rayleigh scattering, that is called as Rayleigh scattering. Okay, Rayleigh scattering. It is found that by Raman, in addition of this frequency, there is, in addition with this, other type of frequency is also there. It may be higher than this incidence frequency or lower than this incidence. Two possibilities there. Okay, we have the h mu s. Okay, the frequency of the scattering light is changed. Okay, we have discussed this scattering light, that is the frequency is mu s, may be more than the frequency of incidence light, or mu s is less than the frequency of incidence light. Okay, your light photon falls on the sample, it's scattered light. That scattered light maybe have the same frequency of incidence light, or in addition with this, some other frequencies observed. It is that frequency may be more than the incidence frequency, or it is observed that may be less than the scattering frequency may be less than the incidence frequency. Okay, this frequency other than the incident frequency is a Raman scattering. That other scattering is called as Raman scattering of light. Okay, if the frequency of the scattering light is more than the incident light, that is mu delta mu. Okay, that is a Raman shift. That delta mu value is called as Raman shift and is given by delta frequency I minus frequency scattering. And if this is the positive one first, if this value is a positive, it means the scattering frequency is less. Okay, therefore that value is the positive. And if the shift is negative, it means your scattering frequency is higher than the incident frequency, and scattering frequency in this case lower than the incident frequency. Okay, if scattering frequency is less than the incidence frequency, that lines is called as Stokes lines. That lines is called as Stokes lines. And if the scattering frequency is higher, then that lines is called as anti-Stokes lines. Okay, therefore for the anti-Stokes lines, delta mu is the negative, and for the Stokes lines, delta mu is the positive. That is, in the Stokes lines, incident frequency is higher than the scattering frequency, and in anti-Stokes lines, incident frequency is lower than the your scattering frequency. Okay, we have seen the basics of Raman spectroscopy. When photon of light is strike on sample, it's scattered light along with the some mu I frequency. There is other types of the frequency is also observed. It may be more than incident frequency. That frequency of light is more than the incidence frequency, or maybe less than that incidence frequency. If incident frequency is higher than the scattering frequency, that lines is called as the Stokes lines. And okay, that frequency is scattered by, is detected by detector, and you will obtain spectra. In that spectra, at the middle line, if that is the Rayleigh scattering frequency is observed, mu I is observed at the middle. That's detector give the spectra. The mu I frequency means the when h mu I strike molecules and is scatter light and same energy, there is no exchange of energy takes place. Therefore that is the Rayleigh lines, and in this side there is a Stokes lines is observed, and right hand side there is a anti-Stokes lines is observed. You found that in anti-Stokes lines higher frequency than your incidence frequency, and Stokes line has the lower frequency than the incident frequency. When your light, we will remove this. If the light is strike on the sample, that is a sample, and h mu I energy is there, and it scattered h mu I frequency, it means there is no exchange of energy takes place. If mu I frequency change, if suppose mu I frequency mu s is there, if change in frequency takes place, it means the energy is exchange takes place. If such situation is there, incident light is falls on the sample, it is scattered light due to falls on this, and scattered light if the frequency of incident and frequency of scattered light is same, h mu I is equal to scattered is also h mu I. It means the energy of incident light and energy of scattered light is same. Therefore, in this case, no exchange of energy takes place. Okay, therefore, if no exchange of energy takes place, it means that collision is called as inelastic. Okay, that collision is called as inelastic collision. In inelastic collision, no exchange of energy takes place. Incident light frequency or energy of incident light will be equal to the energy of scattered light. It means there is no exchange of energy takes place. Therefore, that type of collision is called as inelastic collision. In this, no energy exchange takes place. Okay, second type of collision. Okay, if suppose your incident light, okay, h mu I, is collide with your sample, then scatter light have the change in frequencies takes place. So if suppose at the start it is the h mu I is the frequency. At the last after scattering, the frequency change. Okay, if frequency is changed, it means what? Some energy is absorbed by the molecule, or extra, if frequency is higher, this extra energy is given to this light photon by the molecule. Okay, if suppose mu scattering energy, frequency of scattering, frequency and energy is the directly proportional. Frequency is high, energy is high. If the scattering frequency is more than incident frequency, it means what? The some energy is given by the molecule to that photon, therefore its frequency is increases. And second case, if mu s is less than the mu I, it means the some frequency is some energy is absorbed by the molecule. Okay, such two situation is there. If that photon strike on the molecules, light is scattered, and there is exchange of energy takes place, the scattered light may have higher energy than the incident light, or may have less energy than the your incident light. Okay, that collision is called as the elastic collision. When energy exchange takes place, that collision is called as the elastic collision. Okay, now we will start if your sample is there or molecule is there which is having the mass m and energy E1 and its velocity. Okay, if that there is a sample is there and there is a gas sample, number of molecules is there, they collide with each other, okay, like that, and each having mass m1, E1 is its energy and its velocity is the v1. When photon light, okay, h mu I incidence light, when collide with this molecule, that molecule, due to this collision, it's somehow kinetic energy. We consider if it's kinetic, due to that falls on this, its mass remain m, its energy is changed to E2 and its velocity is changed to v2. Okay, for due to collision of this, it may absorb the energy Therefore, from your it may give the energy to that incident light, that photon. Therefore, its mass remains same, its energy is change, and its velocity is change. Okay, velocity is change, speed is also change. Okay, therefore, the energy at the first that molecule have, okay, by using the law of conservation of energy, we will have the energy of the molecule, a total energy for the system will be that is energy of this molecule E1 plus its kinetics energy mv1 square and plus the energy of photon. Okay, this will be equal to, okay, this will be equal to energy is changed to E2 state plus 1/2 m, its velocity is changed to v1 to the v2 square plus h mu s. Okay, that is scattering of light there. Okay, that's due to collision, that scattering of light takes place. Okay, if we'll start, if there is number of, okay, number of vibrational levels is there, first and second one is there, number of vibrational levels is there, and third one number of vibrations levels is, okay, already we have discussed what is meaning of the vibrational levels. Okay, if suppose your incidence light is falls on the molecule will be excited from V is equal to 0 state to the a virtual excited state, that is a quasi statics excited state. Okay, it's, which is not like that excited. Okay, if suppose we have the electronic energy level in this your vibrational energy level, okay, then again electronic energy levels, and within this you have the vibrational energy level. Okay, that is a vibrational energy level, first electronic to the other energy. Okay, therefore your molecule is goes to the first energy state to the other energy state. Okay, that will give you the vibrational spectra. Okay, but in this case it will not go to that, it will go to the some intermediate energy states. Okay, not in the electronic state or vibrational energy level, not the rotational energy. It goes from that energy level to a virtual energy level, that is quasi static, that is called as the quasi static energy level, which is virtual and which is very unstable state. Within very fraction of seconds it will return to its original state. Okay, therefore if that if your velocity, if incident light frequency is mu I, and if it comes to again at that energy level by emitting energy, okay, mu I incident light, it falls, it's that frequency is absorbed by the molecule, then its energy level is excited from that state to this state, and again it came to its original state by radiating same energy. Okay, that difference is same, therefore that difference is, its mu I is equal to mu s. Okay, mu I is equal to scattering is same. That type of scattering we have discussed, that is Rayleigh scattering, that is called as the Rayleigh scattering. If suppose you are that quasi-static energy state is there, you are by taking the frequency mu I, h mu I is the energy photon, which is having the frequency mu I. When falls on the samples, the energy state of the samples from V is equal to 0 to the quasi excited states takes place, and it again comes to instead of V is equal to 0 state, it will came to the V is equal to 1 state. Okay, it not gives the total frequency absorbed. Okay, it's some energy it holds. Okay, it absorbs some energy, and it will came to the first vibrational energy states. Okay, that kind of energy is associated with your sample, and due to this is the emitted light, and that emitted light the mu s. Therefore mu s, that is scattering frequency of scattering light, is less than the frequency of incident light. Okay, that scattering, okay, that type of the lines observed in spectra, your scattering light frequency is lower than the incident light, and that types of the lines is called Stokes scattering or Stokes lines. Okay, in spectra it is called Stokes lines or Stokes scattering. The frequency of scattered light is less than the frequency of incidence light. If suppose two friends is there, and that friend is given 100 rupees to this friend, and if after some time he asks to him give his 100 rupees, he totally gives his 100 rupees to this friend. That is, if it incidence light, it's excited. Okay, 100 rupees is given. That 100 rupees, that energy is the 100 rupees, and it's again give the 100 rupees, and again the same. Okay, same given and same expected. Okay, same given and the same is expected in a Rayleigh scattering. Okay, same energy is emitted by the sample, same that same photo, same incidence light falls on the sample, is excited, then again re-emit the energy. After the losing the energy from excited state, it will come to the ground state by emitting same type of frequency by mu I incident frequency equal to the scattering frequency. That type of the same given and same taken frequency is the Rayleigh frequency. If suppose it gives the 100 rupees to that friend, but he not give the total, he is only give the 80 rupees to him, some less amount is given to the given is less than the is given is less than the this. If he gives the 100 rupees and he return, given and return there is a difference. If given is more than the return is less. Okay, in this case given is more than the return, therefore some amount is associated, 20 amount is associated with this. Okay, the energy will be associated with this. Okay, that means vibrational energy levels remain quantum vibrational energy levels. Okay, that is levels are the quantum vibrational energy levels. Okay, that energy, that quantum vibrational energy levels or quantum vibration energy is associated with sample. Okay, it's hold that quantum energy vibrational energy level that is absorbed by the sample and that is associated with the sample. Therefore, the scattered light frequency is decreased than the incident light. Okay, in this case. The third case is if you give the 100 rupees to the friends and he return 120 rupees. It means it gives the 100 rupees and he return the 120 rupees. Therefore, the energy is released by that friend. More energy, more money is given by that friend to this. Therefore, this is having 100 rupees at the start. Therefore, it is at the last. It has the 120 rupees associated with this friend, and it is having the higher energy. Okay, therefore, energy loses by this friend, and energy will be associated with this. More energy will be associated at the last to this friend. Okay, therefore, In this case, okay, already molecule should be at the V is equal to 1 state or any other states. Then from by taking the energy, it will go to the quasi excited state, virtual excited state, and it re-emits the energy higher than the given. Okay, therefore H mu I energy is given, and it will give the H mu S energy, and mu S is higher than the mu I. Such condition is the anti-Stokes line. This lines is called as the anti-Stokes lines. Correct? The given is less than the its remit. Okay, it's remit or it's given and taken give the more quantity. Okay, therefore the frequency associated with this mu S is higher than the mu incidence. Okay, therefore for this delta mu, okay, incident light minus the scattering light, okay, incidence light is higher than the scattering light, delta mu is the positive, that is the Stokes lines, that is called as the Stokes lines. Okay, positive, that is called as the Stokes lines. And if delta mu is the less than the delta mu I minus delta mu S, so mu S is the higher, okay, mu S is the higher, mu I is the less, mu I minus mu S is the higher, therefore negative quantity. For this, the Raman shift is negative quantity, and for this 0, okay, mu I minus mu S is 0 is not, that is the Rayleigh's lines. Okay, therefore we have seen the what is meaning of elastic collision. In this case, this is the inelastic collision because energy is not exchanged. Okay, these two conditions, there is a inelastic collision. Okay, the given energy H mu I change to the H mu S. Okay, H mu I changes to the some energy is exchanged, some energy is absorbed by the sample. Therefore such type of collision is the elastic collision, inelastic collision, because the energy is exchanged. Okay, that is we called as the elastic collision, because energy is, that is the elastic collision. In this case, elastic collision, and in this case some energy is absorbed by the sample or the given by the sample. Energy exchange takes place is called as the inelastic collision. In this case also energy exchange takes place, that is called as the inelastic collision. And elastic collision means that there is the energy exchange is not takes place. Okay, now we have applied the quantum mechanics to the this Raman spectra. You found that when your light is collide with the sample, then its first energy E1, its kinetic energy 1/2 mv1 square, and its incident, that energy associated with that photon collide and sample is the H mu I is equal to E2 plus 1/2 mv2 square plus H mu S. Okay, when photon is falls on the samples, the change in kinetic energy is not as much higher. Okay, its kinetic energy is not change more, okay, very less amount kinetic energy. It becomes equal to the first kinetic energy of the molecule equal to the after collision of photons is same, therefore that term is same, therefore that term will be minus. Okay, that term will be minus, therefore E1 plus H mu I is equal to E2 plus H mu S. Okay, then okay, when you look at this first Stokes lines, you found that energy, if you consider delta He, okay, that energy absorbed by the sample is delta E, then we can give the total okay, that's incidence light, we can give H mu I is equal to delta E upon H. Okay, that frequency can be given as mu I delta mu upon delta E upon H. Okay, like that we will take the E1, that we will take, and that's E1 minus E2 is equal to H mu S minus H mu I Then dE1 minus L2 means the delta E. Okay, change in energy. The same quantity H we will remove outside, and delta E upon H is equal to mu S minus mu I. Therefore, mu S is equal to mu I plus delta E upon H. Okay, mu S is equal to delta E. Okay, mu S is equal to delta E upon H. Okay, mu H is equal to delta E upon H is equal to delta S minus Vi. Okay, therefore, if three conditions, we will discuss the simultaneously these three conditions. Okay, we will find that relation. Okay. Okay, this delta E upon H is nothing but your change in, that is frequency. Okay, change in frequency, delta mu. Okay, frequency is that, quantity is nothing but the delta mu plus mu I is equal to mu S. Okay, new quantity will obtain. Mu S is equal to delta V, that is the change in frequency, plus incidence frequency. Mu S is equal to frequency incidence plus delta mu is the change in frequency. Okay, delta E upon is the change in frequency. If suppose delta E is the positive, okay, delta V is the positive, delta V is the positive, then delta mu S is the more than the delta mu I. Okay, this plus this delta mu S will be higher than the delta mu I. Okay, such situation you will observe in a frequency is higher than the mu I. Such situation you will observe in this case, that is called as the anti-Stokes lines. When delta V is the positive, then that line is called as the anti-Stokes lines. Okay, that delta mu is if 0, then delta mu I is equal to mu S, that is the Rayleigh scattering. And if suppose delta mu is the negative, okay, that change, that mu S is the less, delta mu is the negative, then mu I is higher than the mu S, that is called as the your high incidence frequency is higher than the your scattering frequency, that is called as the Stokes lines. Okay, and you will observe the Stokes lines, that is the Rayleigh lines, and this is your higher frequency is the anti-Stokes line and lower frequency is the Stokes lines. Okay, this is all about the Raman spectroscopy. Your vibrational spectroscopy or the microwave spectroscopy is applicable only for the molecule which is having the dipole moments. But Raman spectroscopy is related to the polarizability. Therefore, it is also applicable for the molecule which is not have the dipole moment. Okay, the symmetrical molecule S2 N2 is also Raman act. Okay, by using the vibrational spectroscopy we can find out the symmetry of the molecule. Okay, vibrational Raman spectroscopy, symmetry of the molecule, or we can find out the your rotational Raman spectroscopy. You can find out the internuclear distances. Okay, this is all about the Raman spectroscopy. I hope you got these points. Thank you very much.